Have you ever looked up at the night sky and felt a sense of awe at its sheer vastness? The glittering stars, the distant galaxies, the immense, dark voids in between. It all seems so grand, so majestic. But what if I told you that the secret to all this cosmic grandeur is you found out there in the sprawling darkness? But right here, in the unimaginably small world of quantum mechanics. What if the largest structures in the universe are just cosmic echoes of the tiniest events imaginable? Today, we're embarking on a journey from the infinitely small to the immeasurably vast. We'll explore how the bizarre, almost magical rules of the subatomic world didn't just allow for the universe to exist, but actively sculpted it into the cosmic web we see today. This is the story of how quantum reality built our cosmic reality. Let's rewind the clock, way back, to the very beginning, about 13.8 billion years ago. In that first infinitesimal fraction of a second, the entire universe was a point of energy smaller than a single atom. In this incredibly hot, dense state, the familiar laws of physics didn't apply. Instead, a different set of rules held sway. The laws of quantum mechanics. Now, the quantum realm is famously weird. One of its most fundamental principles is something called quantum fluctuation. Think of it this way. Even in a perfect vacuum, what we might consider empty space, there's no true stillness. Instead, there's a constant, frenetic jitter. Tiny bursts of energy, pairs of particles, are constantly popping into and out of existence, like microscopic static. The universe, at its most fundamental level, is noisy. It's never truly quiet. In the first moments of its life, the universe experienced a period of mind-bogglingly rapid expansion known as cosmic inflation. Imagine this. In a fraction of a second, the universe grew from subatomic size to something astronomically large, expanding faster than the speed of light. This isn't science fiction. It's the leading theory that explains many of the universe's properties. And here's where it gets truly amazing. As the universe stretched at this impossible rate, it stretched everything within it, including those tiny, microscopic quantum jitters. Those fleeting, subatomic fluctuations were blown up to macroscopic, even cosmic, proportions. Tiny ripples in the energy field of the early universe became vast waves, stretching across the fabric of spacetime itself. Think of it like stretching a perfectly smooth, slightly elastic sheet. Now, imagine tiny imperfections, tiny bumps, are constantly appearing and disappearing on its surface. If you suddenly stretch that sheet to be billions of times its original size, those tiny bumps would be stretched out into large, gentle hills and valleys. The quantum fluctuations were the original imperfections, and cosmic inflation was the great cosmic stretch. So, the universe is now filled with these enormous, but very subtle, ripples. What happens next? As the universe continued to expand and, crucially, cool down, another fundamental force came into play. Gravity. Gravity is patient, but it's relentless. Over millions of years, it started to work on these cosmic ripples, the areas that, by pure quantum chance, were slightly to insert the peaks of the waves, had a slightly stronger gravitational pull. They began to attract matter, pulling in the surrounding hydrogen, helium, and the mysterious dark matter. The slightly less dense areas, the troughs of the waves, had a weaker pull and started to become emptier. This is the key. Without those initial quantum fluctuations, the universe would have been perfectly uniform. A smooth, even soup of gas. In a perfectly smooth universe, gravity would have nothing to grab onto. Nothing would ever clump together. There would be no stars, no galaxies, no planets, and certainly no us. The universe would have remained a featureless, boring fog of gas forever. We exist because the quantum world was noisy. We are the children of a cosmic hiccup. Over hundreds of millions of years, those slightly denser regions became much, much denser. Gravity pulled more and more material into these cosmic pockets. The pressure and temperature at their centers grew until a miraculous event occurred. Nuclear fusion ignited. The first stars were born, lighting up the cosmos. These stars then gathered into the first galaxies. The process had begun, all seeded by quantum chance. Fast forward to today, When astronomers point their most powerful telescopes at the sky and map the distribution of galaxies across billions of light-years, what do they see? Not a random scattering. They see a breathtakingly beautiful structure, a vast, intricate network known as the cosmic web. Galaxies aren't just sprinkled through space. They're organized. They clustered together in superclusters, long, thread-like filaments that stretch for hundreds of millions of light. These filaments connect at dense nodes, where massive galaxy clusters reside. And in between these filaments are vast, empty regions called cosmic voids, some of the loneliest places in the universe. This cosmic web isn't just a random pattern. It's a direct, fossilized image of those original quantum fluctuations from the first fraction of a second of the universe's existence. The filaments and clusters we see today are the direct descendants of the denser regions created by those quantum jitters. The great cosmic voids are the descendants of the less dense regions. When you look at a map of the large-scale structure of the universe, you are literally looking at a giant, frozen snapshot of the quantum world. It's an elegant, almost terrifying realization. The arrangement of galaxies across billions of light-years is a direct map of subatomic patterns that were amplified by cosmic inflation. The laws of the very small directly determined the architecture of the very large. This profound connection is the focus of a field called quantum cosmology. Its goal is to create a theory of everything that unites the two great pillars of modern physics: Einstein's general relativity, which describes gravity and the universe on a grand scale, and quantum mechanics, which governs the strange world of atoms and particles. Right now, these two theories are like brilliant languages that describe different aspects of reality, but they can't yet talk to each other perfectly. Yet, the universe itself is the living proof of their union. We see hints of this union in the most extreme places in the cosmos, like black holes. When a massive star dies, it collapses under its own gravity into an infinitely dense point of singularity. Here, mass and gravity are pushed to their limits, and the physics of the very large meets the physics of the very small. A black hole is a place where general relativity breaks down, and we believe a quantum theory of gravity is needed to understand what truly happens inside. So, the next time you gaze at the stars, remember this: you're not just looking at distant lights. You're witnessing the magnificent, large-scale result of the universe's tiniest, most ancient secrets. Every atom in your body was forged in the heart of a star that was born from a gravitational collapse, and that collapse was seeded by a ripple in spacetime. A ripple that was once a quantum fluctuation smaller than anything you can possibly imagine. The immeasurably vast is not the opposite of the infinitely small. It is its reflection. We are living in a quantum-generated reality, a cosmic masterpiece painted with the brushstrokes of pure chance, stretched across the canvas of space. And understanding this connection is, perhaps, the ultimate quest in our journey to understand our place in the cosmos. Thank you so much for joining me on this journey through space and time. If you found this as fascinating as I do, please hit that like button and subscribe for more explorations into the mysteries of our universe. Let me know in the comments what cosmic topic you'd like to dive into next. Until then, keep looking up.